Okay, I gotta show you this. See the console here? I'm gonna start up my server now. You ready? This is a Java application and I'm gonna start the server. There. Now, I shut it down too, but I wanted to time it just to give you an idea of what we're looking at here. The clock time was 39 milliseconds. I mean, that's 39 thousandths of a second. And the actual server startup time was faster than that because that's got a timer and everything built inside it. That is a full Spring Boot app with Spring AI inside, launching in well under 50 milliseconds. Wait until you see all the rest of this. Now, to give you some context, we're building a Star Trek computer. I'm going to use Java 25, the latest long-term support version. I'm going to use Spring AI. In fact, I'm going to use Spring AI 2, which runs on Spring Boot 4. And this isn't actually out yet. I'm using a milestone here, but that's what allowed me to compile with the Graal virtual machine. And I'm going to use the model context protocol to invoke the osquery utility on my Mac. So I'll show you this. Now, first of all, this was all inspired by a blog post you can see here by Daniela Petruzalek, if I'm pronouncing that right. I hope I am. She wrote this really great blog post about how she turned her computer into the USS Enterprise using AI agents. Now, she did it in Python and everything, and I'd never seen this osquery utility before. So I learned about it there. I wanted to port it to Java and then go nuts with it, as you're going to see. So my Java stack will be a JavaFX utility that'll be the voice interface so that I can speak to it and have it translate my spoken text into a text command that will eventually be sent through the MCP server to the osquery tool, which will then investigate the system to find out information about it and then send that back all the way back to the graphical user interface. One ecosystem, microphoned, operating system, and back, all in Java. So this is all inspired by that voice client and the Spring AI MCP server wrapping osquery and a GraalVM native image for the instant startup. First things first, if you've never heard of osquery, it's a utility that runs on pretty much every platform. Looks like this, but the thing it does is that all the data that it collects from your operating system is saved in SQL tables. So you have to read and write SQL in order to work with it. Like what's eating up the CPU? You have to write select name, comma, process ID from processes, order by CPU time descending or whatever. If you want the fan speed, there's a table called fan speed sensors. It's all read-only, so it's safe to hand to an AI, but you do need to learn the tables and the columns and the flavor of SQLite that it uses in order to work this out. What I'm going to do instead is let a large language model translate my English commands into the right SQL queries, drive the osquery utility, get back the result set, and translate that back into English for me. So I can just say, why is my fan running so loud? And it'll write all the SQL, run it, and give me the results. It's a natural language front end on a nice, useful system tool. The other factor is MCP, Model Context Protocol. Now, before we get to that, I need to point out that there are alternatives. If I just want to use, say, Claude Code or Codex or Gemini CLI, they all understand skills. Now, if I go to my GitHub repository here, this is the osquery MCP Server GitHub repository. If I look inside there, you will see that I have a little folder here called .claude and a skills folder inside it and an osquery folder underneath that. And if you take a look at the skill.md markdown file inside, you can see it's really just explaining in text form to the AI tool how to run osquery. There's some available queries that are samples in here, like listing all the available tables or getting the schema or searching for tables by keyword. I gave it the reference, and then that's basically it. I did put in an extra little file here called queries.md to give it a bunch of samples. Like, oh, if I'm asking why my computer is slow or what the CPU usage is or whatever, here's the SQL query, and on and on. Now, I didn't write all that. I worked with an AI tool, specifically Claude Code, to come up with typical queries and that I could add to the skill. So if all I want to do is work with Claude Code or some other AI agentic tool that understands these skills, I'm fine. I can go with that. But to follow the Star Trek analogy a little further, I'd rather use Model Context Protocol as my Universal Translator. Yeah, I'm sorry. But by exposing it as an MCP service, then any MCP client can access it. And that includes various IDEs and all kinds of other options. Now, before I go on, let me prove a point here. See, I started up Claude Code, and I can use that skill simply by saying /osquery, tell me about my memory usage, for example. And it will automatically convert that into the right SQL to invoke on the tables. You can see it doing it here, running the osquery I utility interactive and translating everything back. You can see the JSON being spit out, and it's interpreting that now to give me the actual answer. And eventually you see this is the sort of answer I get. It tells me what the memory usage is and the top consumers of the memory and insight and all of that. So again, if all I want to do was use one of these agentic tools that understood skills, I'd be fine. I could go with this. But instead, I want to do this through an MCP service, and I'm writing in Java. So here in my Spring Boot application is the class osquery service. And this is really very simple. It just has a lot of samples in it to make it a little easier. What I want is to give a command to the LLM and have it realize it needs to make a tool call. And the tool call I want it to make is to pass information to osquery. So assuming osquery is available, I've got a little check for that. In this method right here, I've got execute query, and execute query has the @tool annotation on it. The @tool annotation is from org.springframework.ai.tool.annotation, and it marks a method as a tool in Spring AI. Again, I'm looking at Spring AI 2.0 milestone 2. So what does this particular tool description say? Execute osquery SQL queries to inspect system state, query processes, users, network connections, and other OS data with an example. And you could see that the SQL is passed in as a string, and we return a string as well. And all this is really doing is using this process builder to run a command line utility. The command line utility being osquery I with a --JSON argument to put in the SQL. That's all it is. The rest of this is just formatting and trying to structure it correctly. We're going to get to how you run certain things in parallel and everything a little bit later. But it's a nice simple mechanism that's just saying, hey, run this command line utility for me. Now, all I really need is this one method, but a lot of MCP success comes from making sure that you've written the method names or the descriptions or both in such a way that the large language model recognizes that your query requires those individual methods. So instead of just using a single execute osquery method, instead, if you look at the structure here, I have methods like get the high memory processes, or get the network connections, or get a system health summary, etc. All these different operations, which again, they're just specializations where I'm giving it sample SQL to use for these things. Although on a couple of them, I've got multiple queries going on at once, and I'm using virtual threads for that. We'll take a look at that shortly. In fact, if I use another bad Star Trek gag on this, think of all the other methods as taking the first method and running it through the replicator. sorry, and then customizing them all to do specific jobs for each one. Okay, here I have to apologize a little up front because my graphical design skills are shaky at best. This is an interface written in JavaFX. So I have a single button in the middle, which when I press it will light up red. And then I'll speak into my microphone and it will record what I say, use the Whisper AI utility to convert that into text, and send the command over to the MCP server. So this is an MCP client that I've written as well. And when it gets the result back, down here in this text area, it will update everything. So let's take a look at an example of this. Computer, run a level 1 diagnostic. Working. Yeah, I threw in the sound effect too. So you can see there's the command that I just gave it. So the transcription from voice to text worked fine. Now this was sent over, and now you could see that I'm getting information back on the various methods being called. And now we hit our one and only delay that I couldn't do anything about. This is the actual LLM making the individual calls and synthesizing everything together. The calls to the various osquery utilities are fast. That's not really a problem. From voice to text is pretty fast as well, as I'll show you. And I'm trying to do all these calls in parallel. You see here that I've got streaming working on the return. So everything coming back is being streamed line by line, and therefore you can see the complete output. Level 1 diagnostic complete. Here's a quick high-level readout of your Mac OS system. Check the system health snapshot, uptime, key hardware, on, and you could see that this is a full set of information coming back. Rather detailed there. Now that command, run a level 1 diagnostic, I mentioned I was going to use virtual threads. Here's the example of that. So on the server over here, the description says get an overall system health summary. It had to identify that from my command about running a diagnostic. And you can see in my try with resources block here, I use the new virtual thread per task executor in order to get an executor for CPU, future, and the CPU, the memory, the disk, the network, and the temperature, all executing at the same time. And these are all calling other methods. Well, this one's showing the SQL directly, but the others are showing other methods in the same file, just invoking various ones that I could have invoked individually. This way I'm trying to invoke them all concurrently. But they all look like this one. They all run supply async on the completable future, which means go run and then let me know what you get back on that executor. And it passes SQL to the osquery tool and gives me back the information. And then down here, I've got a multi-line string that stitches them all together. CPU usage, memory, disk space, network connections, all of that with the join command to make sure I get everything back. So that all the methods look basically like that. And the virtual threads make this very, very easy. Now, what about the Graal virtual machine stuff? I mean, Java is fast, but there's always a startup time with any Java application. It can be as short as just a couple of seconds, but on a starship, a 2-second delay during battle might mean a hull breach, so we want to see what we could do about that. You could see that I have the GraalVM Build Tools native plugin added to my Gradle build in this case, and I am running on Java 25 with the Graal virtual machine. Now that's kind of the combination I needed in order to get things to work under Spring Boot 4. I did have to go to the latest one, but then in my Gradle list of tasks here, you can see that there is, under the build category, native compile. I can't just run native compile by itself. I'm using Gradle version 9.3, and unfortunately the wonderful thing they've added with Gradle, the configuration cache, kind of interferes with this native compile stuff. So what I ultimately have to do is run Gradle W native compile with the flag no configuration cache on top of it. Okay, fine. And the result is, if you look in the build folder here, under build, there is my native folder with native compile, and this osquery MCP server is in fact the native executable. And we saw how fast it ran, but let me demonstrate that directly to you. So I'll clear the screen, and just to give you an idea, to show you how fast that starts up when you just are running it interactively like that, there's the direct path to the executable, and by the time I hit the enter key, it's running. I'm going to shut it down again, because in reality, I have it starting up on the client. If I go to the client over here, inside the client interface, it has to get the various tool definitions. In the client, I have a separate GitHub repository. So if the first one was the osquery MCP server, this one is called Starfleet Voice Interface. And I've got my API key in there and everything. And I'm using GPT-5 Nano to keep everything quick, or as quick as I could at any rate. And you can see down here, after I've enabled the MCP client, the command is simply the path to that executable inside the server. So I would just update that to wherever I happen to put that in general. And you do have to specify an args, even though it's empty in this case. So there are no arguments to my executable. I just use the executable and it runs, and this knows where to run that. So here, when I want to process the command, this is what's being invoked by my voice interface, then I have these various consumers that are used because I'm doing things in terms of callbacks with a flux. So I tell it as a system command, you're a system diagnostic assistant for Macs, and you're using the osquery tool, and here's all the things we want to know. When I invoke my tool, then I get back a flux of string. So I say, let's dump each line directly to the interface, and then when we're done, I'll let it know. And if there's an error, I would say that and just subscribe to it. So the rest of these are just ways to get the individual tool definitions. Computer, armed, phasers, and lock on target. So let's wrap this up and talk about what we actually have. I've got this diagnostic capability in a couple different ways. Setting it up as a skill is simply a matter of formatting some skill.md file in the proper format and putting it in the proper directory. And then Claude Code or one of the other agentic CLI tools can handle that. I went with the MCP server, which makes it discoverable by any AI client. And then the voice interface was simply done by using JavaFX and Spring AI calling OpenAI's text-to-speech capabilities. Then the refinement was to go to virtual threads for calls I need to make concurrently. And then also here I'm doing the reactive streams on the way back to try to show more of the fact that we are getting things back over time. Also, it looks more like the old style computers in the 70s anyway, with the little scrolling text. So find it somewhat amusing. And then finally, compiling everything with GraalVM native images, which I was able to do with the server, works out fine because I'm doing almost no reflection or anything like that on the server side. I do recommend Daniela's original post. It really was very helpful. And the GitHub repositories that I use for this, you're welcome to all that code. The links are in the description, as they say. So hope you enjoyed this. Welcome to Tales from the Jar Side, and I'll see you in the next one. Subscribe for more AI and Java related content. Take care, everybody.